So, introduction to node voltage method. So let's consider a simple circuit. We have a voltage source, a resistance is connected, another resistance is connected here, and we have another resistance. And finally we have a current source. Resistance is 1 ohm. Here this resistance is 5 ohm. We have 2 ohm resistance. We have 10 ohm resistance. This is 10 volt supply and 2 ampere currents. Okay. So in node voltage method, as the name indicates, we have to consider the voltages at the nodes, and based on those voltages we have to analyze the circuit. So let's identify the nodes. So as you can just recall our previous lecture, a node is a point where two circuit elements can join. So here the resistance and this voltage source, it is applied. So this is a node. Here it is another node, and here it is another node. And if you look at this point, so all these nodes, apparently these are different, but since they have the same voltage level and they have common interconnection, so we can consider this as one node. So there are 1, 2, 3, and 4 nodes. But the node voltage method is based on the concept of essential nodes. So by definition, if you just recall our previous lecture, that the essential node is that node where 3 or more circuit elements can join. So here, if you look at this node, we have resistance 1 ohm, we have 5 ohm resistance and 2 ohm resistance. So 3 circuit elements can join this node, so we can call this as essential node 1. Look at this node. Again, 3 circuit elements, 2 ohm resistance, 10 ohm resistance, and 2 ampere source is joining. So here, this is also called essential node 2. So I simply mark it node 2. Now look at this node at the bottom. We have more circuit elements which are joining this voltage source, 5 ohm resistance, 10 ohm resistance, and 2 ampere. So all these are joined at one common point, so we can call this as node 3. So simply call this as node number 3. Another step, you can say step number 2, we have to identify the reference node. Okay, so you can ideally you can just mark any node as reference node. If this node can be considered as reference node, this can be considered as reference node, or this node can be considered as a reference node. But just a recommendation is that always take that node as a reference node which has more elements connected. So here, if you see more elements are connected to this node, so we can call this node as reference node. Okay. So now we have 3 essential nodes. If I simply represent this essential node, so LE is equal to 3 essential nodes are there. So how many equations do we need in order to solve this circuit. So this can be determined by this expression, number of equations needed, that is NE minus 1. So here 3 essential nodes, so it means that number of equations are 2. So 2 equations are needed in order to solve this circuit. Okay, so we have defined the essential nodes, we have marked the reference node. Remember, reference node can be determined by this symbol, or you can use ground symbol like this, or you can use this symbol, or some people they just mark it like this, so you can, there is no problem with that. So same node, so it is like that. Okay, now we have to mark the voltages. So here you see at node number 1, let's assume that the voltage at node number 1 with reference to this ground is denoted by V1, and here the voltage with reference to this ground at node number 2 is denoted by V2. Now we have labeled all the circuit elements, the voltages. So now what is left? Just to write the mathematical equations for this circuit. So here we take the help of Kirchhoff's current law, and for each node we apply KCL, Kirchhoff's current law, and we write the equations for that. So the KCL, if you just remember Kirchhoff's current law, it is just states that the sum of all currents leaving the node is equal to sum of all currents entering into a node. Okay, so if we just consider a typical node and we want to analyze that node and writing the Kirchhoff's current law for that node, what we have to do, we will assume that all currents are leaving unless otherwise stated or mentioned in the circuit. So for example, if we consider it here, so we will be assuming that the current is leaving in this direction, the current is leaving here, the current is leaving here. Okay, so at node number 1, at node number 1, so just apply KCL. So we can write this as V1 minus 10 volt divided by 1 ohm resistance. So this is the current, plus V1 minus V2 divided by 2 ohm plus V1 divided by 5 ohm, and there is no current entering, so it is equal to 0. So this is now the equation at node number 1, and simply mark it as equation 1. Now applying the KCL at node number 2. Okay, so at node number 2, assume that the current leaving at node number 2 towards node number 1, so you can write this V2 minus V1 divided by 2 plus V2 divided by 10 and equal to this current, 2 ampere current is entering, so we can write this as 2 and mark this as equation number 2. So now rearranging these equations, simplifying these equations, we can now just rearranging this equation, so we can see here that we have 1 plus 1 over 2 plus 1 over 5 and into V1 and minus 1 over 2 into V2 is equal to 10. Or just taking the LCM and other things, so we have, I think, 17 out of 10. V1 minus 1 over 2 V2 is equal to 10. Or 1.7 V1 minus 0.5 V2 is equal to 10. So this is now equation number 3. And similarly, simplifying this equation, so we can rewrite equation number 2 as minus 1 over 2 V1 plus 1 over 2 plus 1 over 10 into V2 is equal to 2 10. And this is equal to minus 0.5 V1 plus, this is 0.5, this is 0.1, so this is 0.6 V2 is equal to 2 ampere. So just mark it as equation number 4. Now we are ready to solve this equation, and you can use any method. And if you can transform this in matrix form, you can easily solve this. So transforming these two equations into matrix form, just representing these two equations in matrix form. So you can write this as 1.7 minus 0.5 minus 0.5 and 0.6, and this is V1, V2, and you have now 10 and 2. Okay, so solution of matrix is very easy. You can easily solve it. So you can write this as V1 taking the inverse minus 0.5 minus 0.5 0.6 inverse into 10 2. And if you solve, you just taking the inverse, and the inverse is equal to adjoint of this divided by the determinant of this matrix. So after doing all these calculations, you can easily solve this, and the answer here is 9.09 volt and 10.91. Okay, so this is very simple and very easy.